Okay, so we're going to be talking about, in this section, creating and analyzing graphs. So we're going to talk about independent variables, dependent variables, and how to take a set of inputs and outputs and plot them on a Cartesian plane. The first thing that we want to go over before that is a few standards. I'm going to talk about appropriate units and context for the purpose of descriptive modeling. So this is going to be limited to a few scatter plots. I'm going to choose a level of accuracy appropriate to limitations on measurement and reporting quantities. Okay? We want to understand what type of unit we're dealing with. We want to use units in a context as a way to understand problems. And then there is one other standard. Here it is. Kentucky HSF4, graph functions expressed symbolically and show key features of the graph with and without using technology, computer, graphing calculator. So you're going to graph linear and quadratic functions. You won't be doing quadratic functions today. So really this is just barely going to hit the standard. We're just kind of understanding how to take a set of inputs and outputs and graph them on a coordinate plane. So we're going to get right into it. So typically you have an input and an output. So the input you call the independent variable. This is the variable that is manipulated. So a lot of scientists, whenever they're working with problems like this, they're going to pick an independent variable, one that they can manipulate, or observe being manipulated or changing, and see what the outcome is. One particular example would be time. You can watch time pass, and you could observe a population. So if I'm a marine biologist, I can take a look at a population and I can see how they change over time, if they increase or decrease, and model that with a graph. Okay, dependent variable is the variable that changes due to the manipulated variable. Okay, so what I want to do is I want to start with this example, and we're going to talk about appropriate scaling and that kind of thing, but I'm going to do it on this part of the graph. I'm going to flip back and forth. So you want to choose an appropriate scale for whatever graph you are using, and then you also want to label your axes properly. Typically for just generic models we use X and Y, but you're going to see in this case we want our graph to mean something. So we are going to change that up a bit. So I want to make sure that this graph is pretty large. And let's look at those input and output tables again. Yeah. Okay. So we've got a few different things going on here. Which you should notice first is that the input is weight. So the manipulated variable is weight. So as weight increases, we're seeing how price changes for frozen yogurt. And we want to kind of see with our eyes what's going on with the graph over time. As we increase weight. Okay, so we're going to label the two axes as weight. So the x-axis is your input. So that's the first column here. So I'm going to label that first axis as weight. So this is weight in ounces. And then if I take a look at the y-axis, that's price in dollars. So this is price. And then in a lot of mathematical models, what you'll see is somebody will tell you, or the graph will tell you what the situation is. So what are we talking about? Well, we're talking about frozen yogurt. We're talking about the price of frozen yogurt. So I'm going to write that down. And since we've got all of our axes labeled like that, now we want to choose an appropriate scale. Now a scale is like how many are you going to count by for each axis? How much are you going to count by? So sometimes if your values are very large, like in this case it wouldn't be, but take a look down here, like the score for this graph, one's 100, one's 500. If you started to count each tick mark, it's going to be a terrible day for you because you can't graph. It's not going to be easy to graph these points on this axis without labeling these by a different scale. So if I counted by 100, that would be easy to understand where these points are and see the visual graph. But if I counted by ones, if this is 1, 2, 3, and I tried to graph the 0.3 comma 100, I'm going to have a bad day. Up here you'll see that the input is pretty normal, right? I've got some pretty small numbers up to 14, but the output I've got some 50s, 0.5s, okay? It goes all the way to 7. So what I'm going to do is on the y-axis, since I've got some 0.5s, I'm going to count by 50 cents. And then on the x-axis, I might count by 2. So I'm going to show you what that looks like. So I've got 0.5, so 50 cents, $1, $1.50, $2, $2.50, $3, $3.50, $4, $4.50, $5, and then I'm going to extend this up. And sometimes you don't have enough room to do what you want to do, so you just extend that graph up and then you're good. And then I've got $5.50, $6, $6.50, and then $7. And this is still price. Okay? And then down here, if I count by 2s, I'm talking about ounces. So each individual tick is going to be up by 2 ounces. So I'm going to show you what that looks like. So the first one I have is 2 ounces, then 4, then 6, then 8, then 10, then 12, and 14. So halfway in between those ticks, if I have a number that falls in between those, I just put it right in the smack dab in the middle. Okay? So the first point we want to graph is 2, 1.0. I'm going to go right to 1.0 from the origin. So there. I'm going to do this in a different color so you can see it. And then the next one is going to be 5, 2.5. So I'm going to go right 5 and up 2.5. Next one's 7, 350. Next one's 9, 450. So 9, 450. And then the next one is going to be 12, 6. And the last one is 14, 7. So just on 14 and up 7. And that gives us a good visual representation of how the price increases as we increase the weight. Okay? So as weight increases, as the weight gets larger, what you'll notice is that the price will get larger as we increase the weight of the frozen yogurt. So let's try another one. Let's talk about the independent variable and the dependent variable. So you want to choose some appropriate labels for your dependent and independent variable. So the independent variable, the input in this case is time. So a good variable to represent time would be t. Okay? So for this x-axis, do this correct. I'm going to label it t for time. And then for the y-axis, I'm going to label it s for score. Something else to notice is that on that first graph, we didn't use the left-hand side of the Cartesian plane or the bottom of the Cartesian plane. We didn't have any negatives, okay? If I told you that I'm going to pay you to buy frozen yogurt from me, I'm not going to have a successful business. I'm not going to pay you to take my frozen yogurt. Or I'm not going to say that I have a negative 14 ounces of frozen yogurt. It just doesn't happen. It's almost like saying that I owe you yogurt in either sense. So down here, you're going to see that we dip into the negatives, and the reason is because scores can be negative. We can be below 0. So I've got the positive y-axis, or in this case, it stands for score, so the positive s-axis, and then I've got the negative s-axis, okay? So if I come over here, I want to join these points together, and if you take a look at the x-axis, it goes all the way to 25. So a good scale that I could pick for this one would be counting by 5s. Okay, or counting by 2s. I think I'm going to count by 2s again. For the y-axis, I'm not going to count by 1s or 2s. I'm going to count by hundreds. And the reason is you can see that each one of these y values, each one of these outputs is a multiple of 100. Okay? So let's take a look at this. The first point we want to graph is 3 100, so I'm going to label my scales. So this is 2, 4, 6, 8, 10, 12, 13, 14, 15. Started counting by 1s. That was not good. 12, 14, 16, 18, 20, 22, 24, and then 26. And we don't want to go any further than that because if you notice, our last input is 25. And then you can see that the y-axis goes all the way up to 1200, right? The highest value is 1200. The lowest value is negative 300. So I'm only going to go down 300 on my graph and up to 1200. So let's take a look at that. So if I'm counting by 100, I want to come down here at negative 300. Then I've got negative 200, negative 100, 0, positive 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000, and extend that graph up, 1,010, and 1,020. Oh, no, that's not true. 1,100. So 1,100, and then 1,200, right there. Okay, so since I've got my axes labeled, and I know what they mean, I want to label my graph. So the graph, we're talking about scores of Jeopardy. So down here, I'm going to label my graph. This means scores of Jeopardy. So that's just telling whoever looks at my graph what it's about. So as time increases in minutes, the score will either increase or decrease. So let's talk about what we see here. So we said the first point is 3/100. So 3 is going to be right in between 2 and 4. And then I'm going to go up to 100 is what it says. 3/100. So I'm going to do that first point there. And then the next point is 8/500. So 8/500. There it is. Next point is 11/700. So right in between 10 and 12. Up at 700. And what you'll notice is that it's nonlinear. So it's going to change now. I went from 700 down to 200, so 15/200. And that kind of makes sense, right? Because we could lose points in a game like this with penalties and that kind of thing. So I went down from 700 all the way down to 200. So it kind of changed direction there. And then what you'll see is that it takes a turn for the worse. We go in the negatives. We go all the way down to -300. And that was at 18. Yeah. 18, -300. And then we've got 21, -100. So I'm on the rise there. So I've earned some points if this is me playing Jeopardy. And then at 23, you'll see we have 400 points. And then we've got one more. 25, it says I'm all the way up at 1200. So I had a huge boost in Jeopardy. And that's kind of what your graph would look like in this situation. I'm just going to clean up that point. That was 8/500. Make it look nicer. So I kind of went up in score right here, and then I had a bad run here. So I went down here, and then I went to my lowest point, and then I started to increase my score. So as time moves on, this is how my score changed in Jeopardy, whoever we're looking at here. And what you'll notice is that, right, things are not linear in Algebra 1. Things start to become nonlinear. Things start to, and even more so in Algebra 2. And so now we're going to do this kind of backwards. So let's take a look down here. It says Mr. Brust likes to run to work. The table shows the distance Mr. Brust is from his house over the course of his run. Okay? So you got distance from house in meters, and then you got time that goes on. Okay? And over here we want to know what the independent and the dependent variables mean. And then we also want to know how to fill this chart out. So the first one we're going to look at is the x-axis. So if you look at the x-axis, it's labeled as time in minutes. Okay? So we want to know both the unit and we want to know what the variable is. So the input is, let me do this in red. The input is time and the unit is minutes. And let's talk about that standard for a second. Right? That standard was talking about creating appropriate scales. Okay, I can't get to it in time, but if you think about that standard that we were talking about, the N4 and N5 and N6, you want to know what your unit is, okay? You want to talk about what the unit is, you want to know what you're dealing with, so each one of these numbers represents the number of minutes. So this is 3 minutes, that's 3 minutes, that's 5 minutes, that's 7 minutes, it's 9 minutes. So let's take a look at this. And what they want to know is what the output is for each one of these. So I'm going to have to look at my graph, but I want to know what the variable means for the y-axis. So over here, the y-axis is the distance from house. So this is distance. That's what that variable is. So that's the dependent variable. So distance changes as time changes. And then the unit, it says, is meters. So M means meters. Okay? And I want to kind of analyze this graph and see what's going on and figure out the coordinates that go with each value. So the first input is 3. So what I'm going to do is I'm going to look on this axis here and find 3. And I'm going to see where it's corresponding with the y values. So if I look up at this red line, 3 corresponds with 400 here. So after 3 minutes, Mr. Brust has ran 400 meters. After 5 minutes, which is the next line, after 5 minutes, he has ran 700 meters. So I'm at 700. And then we've got 7. And at 7, looks like he's at 800. And take a look at what's going on in the graph, right? He was moving forward, he gained some distance, and then take a look here. There's no distance being gained, but time is running on. So maybe he stopped at the minute mark. Maybe he did something, maybe he dropped something on the way there. Maybe he had to stop and pick something up. Maybe he had to, go get breakfast, so he had to wait in line for a few minutes. So that's 800. And then if we take a look at 9, you can see here at 9, even though we've moved forward in time, our position hasn't changed. So we're still at 800 meters from the house. And then the next thing they give us is the output. So they give us what the y value is, and we have to find what the corresponding input is. So if I go, the output is 1100. So if I look on this y-axis over here, I'm going to go across until I hit the graph there. And I'm going to drop down from that point to see which inputs correspond to that, which in this case is going to be 11. So after 11 minutes, Mr. Brust has ran 1100 meters. And then we've got 1600. So we're going to do something similar with this, but notice that there are 2 inputs for this particular value. So they've given us 2 spaces to work over here, and that's important. If you take a look, draw this in purple. Right there and right there is where Mr. Brust is 1,600 meters from his house. So the question is what happened from here to here? And I can tell you from my experience running, I was running with my daughter one time. She was in a stroller, and she had a little toy. Okay, so when I ran forward, she dropped the toy. She dropped it like right here. So what I had to do was, she's crying about it, so I had to run back and find that toy. So I stopped for a second and looked around and then found it and then came back and started running again. So maybe that's what's going on here, but you might be wondering, okay, why did you lose distance? Well, if you think about it, if I drop my keys and I'm walking forward, I have to go back and get those. So I can think of that as negative distance. I'm coming back to my house. I'm coming back toward my house. So maybe that's what's going on here. So you can kind of ponder about those things. But if I drop down from those 2 points, right? 13 is where they did the sharp turn. Mr. Brust did the sharp turn. He had to go back. Didn't even skip a beat, didn't even stop. He just turned around and went back. So 13 minutes. And then he came back to 1,600 meters from his house, that point he turned around at 17 minutes. And just considering all this, thinking about 20 minutes and thinking about the distance he went, this is really, really slow. This is almost a walking pace. I used to run cross country, and so typically you're going to run a 5K, which is about 3.1 miles. So this is a little over 1. So in 19 minutes, it seems like he went a little over 1 mile. And yeah, we can factor in this little section here as an extra 200 meters. But still, we're not getting very far. And then we've got this little question. They want to know what the point 1800 means. So, well, if I think about 18, if I look at 18 is time. So it means after 18 minutes, Mr. Brust has ran, and I want to know where that is. Just double check that work, because it says the output is 1800. Let's just check. And he didn't run that far, actually. This is the distance from his house, so Mr. Brust is 1,800 meters from his house. Okay? And then we've got this little story time. It says Professor Splash set the world record for a 36-foot belly flop into a 1-foot pool of water. That sounds very unfun. Sketch a graph of his height over time. So if I want to think about somebody that's going to dive into a pool, I don't know how you become a professor of splashing, but right, there's our diving board. And here he is. I'm just going to draw him muscular, because if you're going to hit, he's very strong. If I'm going to hit the ground or hit this water that's 1 foot deep, I'm going to need to be a little tough. And we're saying world record with a 36-foot belly flop. So what this is saying is at his maximum height, he's 36 feet in the air. But if you think about it, if he's jumping off of a diving board, he's going to go up. Okay? He's going to go up after he's jumped, and then he's going to come back down after gravity takes hold of him. And then there he is, and he just splats. He's got skinny legs, like me. And he just hits the water. So we're saying that this distance here, this distance is 36 feet. And then this distance down here is 1 foot. So that's kind of what we're getting into. So just, right, a lot of times whenever you're doing graphs or any type of work like this, you are doing it in context, okay? Just graphing is not going to make any sense except for rote memorization and knowing how to do it. Looking at a context like this is going to tell you what's going on with the story. It's gonna kind of get your mind thinking, okay, this means something. And that's what math is about. It's about kind of describing the world, and that's what I want to get into with Algebra 1. So the rest of this is practice. If you need some more help, I will go over some problems. Other than that, this one's up to you. So that is all I've got to say.